Hello, welcome to another mathematical studies video. I'm going to finally use a chi-square statistic to check for independence. Now again, I need two variable data, and I'm just going to check whether the data is dependent on each other or whether it's independent. This will be the last video on the chi-square statistic. So suppose that I have somebody and they're going to be checking whether getting a tutor makes people get better grades in math studies. They're looking for causation here, but we're going to be trying to determine dependence, whether it's dependent, whether one thing is depends on the other. So there's two hypotheses, two possibilities. One is going to be called the null hypothesis, and it says this, that the grades students get and getting a mathematics tutor are independent. There's no relation. The alternative hypothesis to this is the opposite thing, which is to say that they are dependent. So the chi-square test will let me know which of these two is the one I should choose. So I have to compare my chi-square statistic to the critical value and determine which one should I keep. If the chi-square is smaller than the critical value, we can't rule out the null hypothesis. We should accept it. We should say, well, with this data, I should accept the null hypothesis. If it's bigger, however, I can't rule out the null hypothesis and say, well, I think they're going to be dependent. My data is saying that these values are dependent. So this is actually going to be very important. So how do we do it? Let's have an example here. Again, I have the values here of math studies and people who got a private teacher and people who didn't. This is what it looks like. Great. So let's set the hypothesis. The null hypothesis is going to tell me that the grade students getting mathematics tutor is independent, and the alternative hypothesis is telling me the opposite, that they are dependent. Now I calculate my chi-squared value. They're giving me the critical value, which is 12.592. I calculate my chi-squared to be 1.82, as we did in the previous video. And since it's 1.82 is clearly much smaller than 12.592, we should accept the null hypothesis and reject the alternative hypothesis. Hence, I would say, as a conclusion, that the grades students get and getting a mathematics tutor are independent of each other. That's the example. Now, let's understand a few limitations. Now, we are kind of done with the chi-squared. But I have to mention a few limitations that this has. This is particularly relevant towards your internal assessments. So be aware of the following important limitations. On my table, I can't have an element in more than one place. If, for example, I had a student who got a tutor and then didn't have a tutor anymore, and I decided to put the student in two of the slots, right? He got a 4, and I put them both in the didn't have a tutor and it did have a tutor. That's an element that's in more than one place. I can't have that. The chi-square will not work properly, and the values that I'm going to get are not going to be correct. Another important thing is I need to have more, I need to have quite a lot of data. I can't have frequencies, like a lot of frequencies that are under 5. The rule is the following. If it's a 2 times 2 table, expected frequency should be over 5. If it's larger than that, they should always be over 1, and more than 20% should be over 5. When the degrees of freedom is 1, the chi-squared value is going to give me something that's too big. And I have to use the Yates continuity correction to fix it. Now, you don't need to know this. It's relevant towards your internal assessment only. One important thing to note here, if I have this situation here, I can group the data so that I can use my chi-squared test. Remember grouping the data from descriptive statistics. I just put it together and say, for example, 1, 2, 3. Anyway, let's go back to an example to close the loop, tie the knot, and finish off chi-square statistics. So I have international school in Madrid with Spanish students and foreign students. All the students have to choose a sport to practice, and here are the choices they make. So 43 students, local students choose football, 29 choose basketball, and it seems that there's more foreign students that choose basketball and less than choose football. So a student called Cecile wants to check with a 5% level of significance whether the sports choice is dependent of the student's origin. Now I'm trying to make here what perhaps would be an exam question. The first asks me to state the null hypothesis, which is simply to say that they're independent. The choice of sport and their origin are independent, the origin of the student. The number of degrees of freedom, now I can do this with the calculator, but I'm going to do it without it for a minute. Now, there are only two values that are independent of the totals, which are these two here. This one here, I can calculate it the moment I know how many local students I have in total, and these two are filled up. And the moment that I know how many students in total play football, I can calculate this one and this one. So the only values I can put in freely are these two, hence degrees of freedom is 2. Now I'm going to have to calculate the expected frequency for local students who play basketball, expected frequency, p-value, and then whether I have to reject or accept the null hypothesis. Let's first calculate the frequencies when I put the expected frequencies. Now, when I calculate the chi-square with the GDC is automatically going to do the expected frequencies for me. So I've inserted the values in the 2 times 3 matrix. There they are. I calculate and realize how it's going to put the expected in B. I don't have anything here. The calculator is going to do it for me. Now I go back to the matrix menu once I have calculated it, and I will find this. You see how the graphic display calculator filled up the expected frequencies for me. Now they wanted local students who play basketball, the expected frequency for that, so it's here. And I can say the expected frequency of local students who play basketball is 34.197. Finally, I can calculate the p-value. I click calculate again, and here it is. This is the p-value, 0.178, approximately 0.1793 significant figures. And finally, they asked me to whether we should reject or accept the null hypothesis. Note, I could have calculated degrees of freedom this way, by the way. Anyway, we say that she should not reject the null hypothesis since 0.179, the p-value got here, is bigger than the significance level. And that's exactly why we should not reject the null hypothesis, and instead we should reject the alternative hypothesis. This time around, we've done it using the p-value rather than the critical value because it never gave it to us, so we couldn't use it. Well, this is an example of how an exam question might be. We'll do some more exercises, but all in all, this is all you need to know. Thank you very much for watching. Goodbye.